Hello, dear members. Today we are going to be discussing signals. So signals are talked about especially in engineering and in areas of communication and even in mathematics. So we want to understand the mathematics behind a signal and how is it different from a function. So we shall see that mathematical function is any general mathematical concept that maps inputs to output. It can be defined in any domain, and that is real numbers or complex numbers. So imagine having a function such as f of x equivalent to x cubed plus, for example, 3x squared plus maybe 2x plus 4. You see that this function does not necessarily represent a physical signal. In other words, it may not represent a physical quantity. But let's look at what a signal does. A signal is a function that represents the variation of a physical quantity over time or space. Signals are often used in electrical engineering, communication, and physics. So you'll find that actually a signal is a subset of functions because it also maps inputs to outputs. But here we are talking about a physical quantity, okay, that varies over time or space. So we can say that actually all signals are functions, but not all functions are signals. So we're talking about a quantity varying with the time or space. That can be a signal. But you can also have a function that is varying. You find it is representing a quantity varying over time and space. But not all functions, okay, are signals. As you can see, this one doesn't really represent any physical. It may not represent any physical quantity, but you can see it is mapping inputs to outputs. You have f of x that is dependent on a value of x. X is the input, f of x is the output. So any quantity that is varying over time and space is actually going to be a signal. So anything that is varying over time or space is what we are going to be calling a signal. Yes, so that is a difference between a function and a signal. We are talking about quantities varying over time. So let's look at an example. You have an electrical voltage that is varying over time. So you can have such a quantity like voltage, which is a function of time, equivalent to 5 exponential or maybe negative t out of 2, and then maybe cosine of 10t. This one, you can see it represents a signal because it is a quantity that is varying with respect to time. Then you can also have it a signal in terms of a digital bit stream, where you have the signal represented as a digital signal. It is actually discrete. You find that the values of the signal are finite, whereas this one, you see it is a continuous signal, and this one is discrete. So in plotting this, you can find that if this is time and this is f of t as a function, it can vary. But you can see this one is going to be having discrete points. You have a 1, now you have a 0, you have a 1, you have a 1, you have a 0. So this becomes also f of n, whereby this is n. At n is equal to 1, you have the output. N is equal to 0, you have the output. So this becomes also a discrete signal, which has, it is a signal in form of a digital bit stream. So let's look at types of signals. Now, we said signals are quantities that vary over time or space. So we have those signals that are time-dependent signals. They are expressed as functions of time. So these signals change over time and are common in electrical engineering, acoustics, and communication. So you can see that with the audio signal, speech or music, you can have an a signal represented by maybe x of t equivalent to a cos or maybe 2 pi ft then plus phi, whereby phi is just a phase angle. So this is seen in the pure musical tone. You find that this is a sinusoidal signal where F is actually the frequency. F is the frequency in hertz. Applications, you can see it in the microphone recordings, radio signals, sound waves, even as I'm recording myself. This can come as a sinusoidal wave signal. Then let's look at the voltage in a circuit. So voltage in a circuit can be represented by, for example, V of t equivalent to 5 negative t out of 2, then cos of 10t. This can be seen as a voltage in a circuit, and you can see it is a signal. Then this can represent a decaying oscillation in an RLC circuit, resistor, inductor, and capacitor circuit. Then the applications obviously in the electrical circuits and communication signals. Then we also have a digital pulse signal like we had earlier on seen. So we can have f of n in form of a digital bit stream. So this is going to be like 1, 0, 1, 0, 1, 1, and so on and so forth. So obviously this is in a digital communication and data transmission. Usually we find that it is safer to transmit information or data in terms of digital pulse signal other than having it as an analog signal, because analog signals are affected by distortion and interference and very many effects on them. So the quality as transmitted originally may not reach the final destination as desired. But when you send it as a digital signal, then it is able to reach and in a required quality that you desire. Then we have space-dependent signals. Those are now functions of X, Y, or Z. These signals change over space and are common in imaging, physics, and wave propagation. In imaging, you'll have an image, and this image it will be actually having points in space, such as Y and X. So, understanding this, you find that you need what? You need to understand that actually this is space-dependent signal, and even when you want to work on it, this is what you should work with. So that is like an image signal, okay? For example, a two-dimension Gaussian intensity function represents a broad light spot. Applications, we see this in computer vision, medical imaging, such as the magnetic resonance imaging and the computed tomography. All of these are using images, and those images are represented in terms of space-dependent signals. Then we have also the temperature distribution in a rod. Temperature distribution in a rod also is a space-dependent signal. So you can have temperature T of X equivalent to 10, maybe 100 exponential of negative X out of 10. So you can see this is dependent on the displacement from one point to the other in a metallic rod. So this is showing you how temperature is distributed from one point to the other on a metal rod. Temperature along a metal rod cooling from one end. So this is seen in heat transfer and thermodynamics. Another space-dependent signal is seen in electromagnetic wave in free space. So such a signal can be represented as, you see, you have electromagnetism, and this is giving us E naught cosine of kx minus omega t. And so such a signal, you can see it is dependent. This is dependent on both time and space, but you see it also has some space. So a traveling electromagnetic wave and represented by such an equation, we can see this in fiber optics, in radar, that is radio detection and ranging, and wireless communication. So as we have already seen, time and space are combined. So we form combined time and space signals, and those are functions over x, y, and time. So some signals depend on both time and space, such as waves propagating in a medium. So waves propagating in a medium can be represented by, for example, if you have water waves, so water waves can be represented by such an equation equivalent to, again, you can have A cos maybe kx minus omega t. So this one, you can see it is depending on space, that is x, and time. Then you can also see this in sound propagation. You can have a sound wave moving through air, and this can be represented by such an equation. So the other point is going to be heat diffusion in a surface. So heat diffusion in a surface can be represented by T of x, y, t equivalent to exponential of negative t sine x and then cos y. So this one can be visible in a heated plate cooling over time. So these are the signals and the types of signals that we have in a real practice. And then I believe in this discussion, you have been able to understand the difference between a signal and a function. We have seen that in summary, signals, we have physical quantities such as voltage, you can have temperature, you can have pressure. So these are physical quantities changing with respect to time, and space. But a function is a general mathematical concept that maps inputs to outputs, and have already seen that all signals are functions, but not all functions are signals, because not all functions are representing physical quantities changing over time and space, or just changing over time. Thank you for listening.